Hi guys, so today we're going to look at exponential functions. Now some of this you saw back in Algebra 1, so some of this might be a review, but really the big thing today we're going to look at is growth versus decay and then doing some transformations. So we're going to start with just the basic difference between exponential growth and exponential decay. This is something you probably saw back in Algebra 1. So the basic parent function, if an exponential function is showing growth, it's going to have a horizontal asymptote and it's going to have this general shape. And this is probably one that you saw back in Algebra 1. Now, some of the points that are on this graph, 0, 1 was a point, because anything to the 0 power is 1. Now, what's different here is that base really can be any different number. Now, we're specifically looking at a case where that base is greater than 1. So let's say whatever that base is, it's 2, it's 7 over 2, it's 5, it's 11, okay? It's some number greater than 1. So 0, 1 is a point on that graph. 1 comma, whatever the base is also a point on that graph, because anything to the first power is itself. And then a third point on this graph would be negative 1, 1 over the base, because that negative exponent would flip it. Now let's say, though, that a base was something in between 0 and 1, like 1/2 or 3/4. Well, then that function is going to show decay. It's still going to have that asymptote. And the reason it has that asymptote, no matter what value you plug in for x, it's always going to be an exponent. And there's no number that you can raise this to that's going to give you a negative as a result. Okay, it can get smaller and smaller and smaller and bigger and bigger and bigger, but it's never going to actually be a negative number or be 0. All right, so some points that are on the decay function again, still 0, 1, because anything to the 0 power is 1. You'll also have 1 comma the base. And then you again would have negative 1, 1 over the base. Now the reason, though, that it shows decay is because of what those negative exponents do. Let's say your base was 1/2. Well, 1/2 to the negative 1 is 2. 1/2 to the negative 2 is 4. 1/2 to the negative 3 is 8. So as I get more negative, those y values are getting larger. All right, so let's talk about the base for a second. So if you notice, one case is that the base is greater than 1. Another case is that the base is between 0 and 1. There aren't any cases where the base is negative. Now you may see some functions that look like this, but that's not a negative base. That is 3 to the x power, and then it is negative. There's a big difference between that and this, because negative 3 to the x power, that's actually not an exponential function, and you're not going to graph these unless that base is a positive number. Because what's going to happen here, if you plug in 1, you would get negative 3. Then if you plug in 2, you'd get positive 9. Well, then if you plug in 3, you'd get a negative 27. And then a positive 81. And then you're just going to kind of go back and forth and back and forth. What's even weirder is when you get to your fraction exponents, if I try and take this to the 1/2, well, that doesn't exist. Or if I try and take this to our negative exponents, we're going to have some of the same problems. So we're not going to graph bases that are negative. All right, so let's look at some basic examples here. First thing we're going to do is just determine, hey, is this growth or decay based on what the base is? Well, for A, my base is 3, so this is showing growth. So the shape of my graph, still going to have that asymptote. Going to move this way. Goes through the points 0, 1, 1 comma the base, which is 3, and negative 1, 1/3. All right, if the base is 3/4, that shows decay. Still has that asymptote. Moves this way. Goes to the points 0, 1, 1 3/4, and negative 1, the reciprocal of that, which is 4/3. All right, next one, all of a sudden we have that a value in front. So that a value is going to affect a lot of these points, but in particular, it's not going to go through 0, 1. But it is still showing decay because the base is still 3/4. But the points that this graph goes through will be different, because if I plug in 0, 3/4 to the 0 is 1. 1 times 2 is 2. If I plug in 1, 3/4 to the 1 is 3/4. 3/4 times 2 is 3 over 2. If I plug in negative 1, 3/4 to the negative 1 is 4/3. 4/3 times 2 is 8/3. So it still shows decay, but it's just that a value in front changes the shape of your graph a little bit. It would be a vertical stretch when we actually start talking about transformations. All right, next graph that also shows growth because that base is greater than 1. So that would go through 0, 1, 1 5/4, and -1 4/5. All right, so what we're going to do now is we're going to look at a different kind of base. So this is a very important number going forward, and that is E. So E is Euler's number. E is kind of like pi, where it actually stands for a very long number with a lot of decimals to it. So one way that we can estimate E is from this expression right here, and it says as x approaches infinity. So as those x's get bigger and bigger and bigger, this number is getting closer and closer and closer to infinity. So let's say I start by taking this expression and I plug in 10 for x. So if I plug in 10 for x, I'm going to get 2.5937. Well, let's take that same expression and plug in 100. So I'm going to get 2.7048. Let's say I plug in 10 to the third. I plug in 1,000. I would get 2.7169. All right, let's say I plug in 10 to the fourth. 2.71815. 10 to the fifth, 2.71827. Plug in 10 to the sixth, 2.71828. So what you'll notice, the farther this goes, the more digits stay consistent. So once I hit 10 squared, it was always 2.7. All right, once I hit 10 to the third, it was always 2.71. Once I hit 10 to the fourth, it was always 2.718. So the farther we go, the closer we get to estimating this value. And that is going to be kind of our best estimation, 2.718. Another way you can estimate it is using this formula with factorials. So if you remember from back in geometry, factorials, 3 factorial means 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. So if you add up all those fractions, 0 factorial, by the way, is just 1. So 1 plus 1 plus 1/2 plus 1/6 plus 1 24th plus 1 over 20. And if you keep adding up, 120. If you keep adding those up, the more and more you add, the closer and closer and closer you're going to get to the value of E. So something that's kind of unique about E, and this will be really important going forward. If you take a point on that function, so e to the x is going to look like your exponential function. And I don't know how I just erased. There we go. If you take any point in that graph, let's say we take this point right here. If I find the tangent line at that point, if I find the slope of the tangent line at that point, the slope of that line is actually going to be the exact same as the y-coordinate of that point. And that's going to be true for any point on that line. And that's a really unique thing about that graph that's going to be kind of helpful for you guys in calculus. All right, so now we're just going to do some exponent review. E is a base, so anything you would do for x to the something power, we can do the same thing with E. Just remember, E does actually stand for a number. It's not just a variable. So e to the third times e to the seventh, we add those exponents. All right, if we're dividing exponents, we subtract. And then here, the 2 would get raised to the 5th power as well as the e. And then because of that negative exponent, we would move that down to the bottom of the fraction. All right, so now when it comes to our exponential function graphs, what can be a little bit tricky is there's more than one way to show decay. One way that we talked about with decay earlier is with the base. All right, if our base was less than 1, in between 0 and 1, then that showed decay. Well, some models that we'll use for exponential growth and decay will have a base of e. E is obviously greater than 1, but we can still show decay with a base of e. And the way that we can do that is by the exponent. So e to the x, just going to look like normal exponential growth. But if I have e to the negative x, even though that base is positive, it's still showing decay because of that negative exponent. So let's think about transformations here. If it's near the x, it's horizontal. That's a reflection over the y. All right, let's think about this a different way. Based on this same idea, 2 to the negative x would show decay, and it does, because it's reflected over the y. Well, 2 to the negative x is the exact same function as 1/2 to the x, because 2 to the negative x is 2 to the negative 1 to the x, and 2 to the negative 1 is 1/2. So both of those ways are different, are forms of showing decay in an exponential function. All right, so let's go ahead and actually do our transformations. All right, so f of x minus h, shift to the right. So what that looks like with exponential, I'm going to go ahead and use a big capital B for the base. Because with exponential functions, again, our base can kind of be anything. What the base is kind of depends on what our function looks like. But all of our horizontal transformations will happen in the exponent. So if it's in the exponent, that's going to be your horizontal changes. And I'm using a capital B because we're so used to using the lowercase b for our horizontal shift, or our horizontal stretch and compression. And again, like we just talked about, a reflection over the y would be a negative in the exponent. A reflection over the x would be a negative outside. And again, it is not what's being raised to the power. It is negative, and then the base is just that number. Again, all of our vertical changes will happen, again, away from the base. And those are our vertical changes. So besides the different bases, something else that's pretty different about these exponential functions, until this point, we've kind of followed the same method for graphing. We kind of follow this pattern. We kind of shift our 0, 0 point, and then we look at our parent function in relation to that point. We still can do the same thing with exponential. But what's different is that 0, 0 is not actually a point on the exponential function. Before this, 0, 0 was always the vertex, or 0, 0 was the point of inflection, or the starting point of the square root. But for exponential, it's not even on our graph. So we can still follow this, but what we're really going to move, I call it the center of the asymptote. We're really relocating the origin, and we're putting everything in relation to our new origin. The reason this works is because if I shift left and right, if I have shifts and reflections and compressions, 0, 0 isn't affected by any reflections or compressions. Because if I multiply anything by 0, it's still 0. So 0, 0, the origin, or whatever that original point was, is always just going to be affected by those shifts. So if we follow the same pattern that we've been doing for these graphs, then that pattern, what we're going to do, it's going to look a little different again. So the first thing would be 0, 1, because anything to 0 is 1. The next point, though, would be 1 base. So that will be different depending on the base of your exponent. The next one would be negative 1, 1 over the base. And the last one would be 2 base squared. Now, in order to have a good graph, you really only need 3 points. This is 4 because it's just a matter of which ones you think are going to be the easiest to graph. There is another method that we can use for graphing, and that's just transforming those key points. This is what we did at the very beginning of the year when we first looked at transformations. So I'm going to show you guys both ways. I like the first way better because that's how we've been doing it for most of the year, and I think it's a little bit faster. But this second method, it's a little bit nicer if you want exact points and you're getting a lot of fractions or hard to determine points. So if you need those exact fraction points, then this transformation process is a little bit easier. But those points that we're going to do would be 0, 1, 1 comma the base. They're going to look pretty familiar. Negative 1, 1 over the base, and 2 base squared. But we also have to consider that these transformations are going to affect the asymptote. All right, so let's go ahead and look at a graph, and I'm going to start with the pattern graphing. Oh, I lied. Did this in class every time too. We're going to go ahead and just identify some features on these first. All right, so the first feature we're going to look at, we're just going to determine the base and the transformations. So my base here would be a base of 7. 7 is not a stretch or compression. 7 is just the base. Transformations that I have here, just left 1. Now, if you look, every function that we've graphed so far that was exponential had a domain of negative infinity to infinity. Range is going to be dependent on 2 things. 1 is where the horizontal asymptote is, and 2 is was this graph reflected over the x-axis. So your graph is either going to be going up or down, and that's going to affect your range. In this case, it was not reflected, and your asymptote is still at 0. So your range is from 0 to infinity. All right, let's look at B. So the base here is E. That 3 then is a vertical stretch. And then this graph has shifted down 5. Nothing is going to change the domain on an exponential function, but range, because it's shifted down 5, that horizontal asymptote is now at -5. And because this graph has not been reflected over the x-axis, then this graph is going to go from -5 to infinity. All right, now let's look at our base. Now this should be a 3 or 4 in parentheses. So that means our base is 3/4. That 4 would be a horizontal compression, and this graph has shifted up 1. Domain is the same, has not been reflected over the x. So that shift up 1 is going to go from 1 to infinity. All right, so let's go ahead and actually graph one of these functions using our transformations. So the first thing we look at is we're going to look at our shifts. We've gone left 3 and down 1. So that is going to be the location of our new 0, 0. So what I'm going to do is I'm going to make a little star at that point. So again, this is not actually a point on my graph. It's really where I've kind of shifted our origins to. I've kind of shifted those axes. So what that means, where that star is, that's where our parent function points are in relation to. So whenever we make that pattern, it's going to be from -3, -1. It's very similar to what we've done before with the vertex, point of inflection, etc., but it's not actually a point on the graph. What we do have, though, is the location of the horizontal asymptote. So we'll go ahead and graph that. So from this point then, we'll go ahead and write what the parent function would normally do. So from this point, we would go over 0, up 1, 1 comma the base, in this case the base is 2, -1, 1/2. We also could do 2 squared, which is 4. All right, so then we look at what stretches, compressions, and reflections we have that are going to affect these points. Because those stretches, compressions, and reflections, they don't affect 0, 0. All right, that's why we just went ahead and shifted them. Well, that negative is going to affect it. That's a reflection over the x. Reflection over the x is going to affect that second number. So from that star, I'm going to go over 0 and down 1. From that star, I'm going to go right 1 and down 2. From that star, I'm going to go left 1 and down 1/2. And from that star, I'm going to go right 2 and down 4. And that gives me enough good points to see my exponential function. Now, the other method we could use, like I said, it's really good for giving you exact coordinates. It takes a little bit longer, and there's some possibilities of messing up your math, which is why I kind of like this first method better. But this is a good review from what we did at the beginning of the year. So what we do is we look at our transformations. So our x's, what's changed to our x's from the parent function is we've gone left 3. Algebraically, that means I want to subtract 3 from the x coordinates of the parent function. All right, let's look at our y's. We're reflecting over the x and shifting down 1. That means I would take the y coordinate, make it negative, and subtract 1. So I'm going to do those same things to those points on the parent function. So those points are 0, 1, same points that we just wrote. All right, and then if I apply these transformations, we'll get the actual coordinates of the points on our graph. So 0, 1, if I take the x coordinate and subtract 3, that's -3. Negative y minus 1, that's -1 minus 1, which is -2. Well, -3, -2 is a point on my graph. We'll do it again, 1 minus 3. Sorry about that. That's -2. Then -2 minus 1 is -3. -2, -3. That's the point on my graph. -1 minus 3 is -4. A negative -1/2 is 1/2. 1/2 minus 1 would be negative. And I just realized that shouldn't be a -1/2. Sorry, the original one was +1/2. So a -1/2 minus 1 is a -3/2, which is, again, a point on my graph. 2 minus 3 is -1. -4 minus 1 is 3. And -1, again, man, I'm sorry, guys. I wrote the transformed points, not the original. The original parent function points should have been 2, 4, and negative 1, 1/2. Because, again, those are my original purple points here were. So negative 4 minus 1 is negative 5. And negative 1, negative 5 is, again, a point on that graph. So that's just how we can get kind of those exact coordinates. All right, let's go ahead and do another one. So I'm going to use that first method just because I think it's a little bit faster. But in order to do that or apply those transformations, whatever's in front of the x, I need to factor it out. So I'm going to rewrite that. So now I can tell I've gone right 6 and up 1. So that little star where my kind of new origin is going to be right 6 and up 1. That tells me where my horizontal asymptote is. From that point, 0, 1, 1e, I'm just going to round it to 2.7. And then I've got negative 1, 1 over e, which is going to be a pretty small value. Okay? Then, transformations, I have a horizontal stretch. That means I'm going to multiply those x's by 2. So from that star, over 0, up 1, right 2, up 2.7, and then left 2, down a very small number. And there's my graph. All right, let's try 2 more. So again, seeing where we've shifted up 2. That's my new origin. That's my horizontal asymptote. So from that point, our typical points are 0, 1, 1 base, negative 1, 1 over the base, and 2 base squared. The transformations I have are both horizontal and vertical. Horizontally, I've reflected over the y. Vertically, I've reflected over the x and compressed by a factor of 1/2. So from that star, I'm going to go over 0, down 1/2. I'm going to go left 1, down 2, right 1, down 1/8, and left 2, down 8. All right, and then last one on there. Again, our base is a little different. Let's go ahead and do our shifts. We've gone right 2 and down 4. That's my new location of my new origin. So from that point, right 0, up 1, 1 base, negative 1, 1 over the base. And this time, to make it a little bit easier, I could do 2, 1/4. That's kind of hard to graph, though. I'm going to do negative 2, 4, because 1/2 to the negative 2 is 2 squared, which is 4. And that'll just be a little bit easier to graph. Transformations, we have a vertical stretch by a factor of 3. And then from that star, these are my new points. So over 0, up 3. Right 1, up 1.5. Left 1, up 6. And left 2, up 12. And that is my exponential function. All right, so again, the method you use for graphing is really up to you. I mean, at the end of the day as well, if you want to pick values for x and plug them in, that is a no-fail way of graphing. So you have a lot of different ways to do it. This is just the method I prefer because I think it's a little bit faster, and it really helps remind you what the parent function looks like.